Give it a moment for the attendees to populate. Good afternoon, everybody. I hope you're not too sleepy after eating lunch. Thanks for being with us today at the Minnesota GIS LIS Consortium Annual Conference. I'm Jerry Goodwin, the student moderator today. I'm a grad student majoring in data intelligence at St. Mary's University down here in Winona. Remote sensing is our topic. Kent Park will be discussing battling cheatgrass through Lidar and Imagery, and Leif Olbenson and David Porter will be discussing advanced remote sensing methods for water quality monitoring and spatial temporal trend analysis in 10,000 plus Minnesota lakes. Please address your questions to Kent, Leif, and David via the Q&A feature at the bottom of the Zoom screen or the chat box if you prefer. Any technical issues, please contact me via the chat box, and a reminder that these sessions are being recorded. Also, don't forget about the virtual Mappy Hour at 4 o'clock. And with that, thank you all, and I'll let Mr. Park take over.
Thanks, Jerry. Hopefully you can see my screen now.
Yes.
Excellent. Well, thanks again, everybody, for being here. I wanted to talk a little bit about some remote sensing work that I've done and been involved with for the last few years. We always like to see and hear about the great imagery and LiDAR projects and how we can use LiDAR to look at elevation and drainage. And here's just kind of a little different take on some studies we've done and actual projects we're doing across the country at this point in time. So the presentation is focused on cheatgrass. I've actually done this with several different varieties of invasive species and go into a little more detail on that here as we go through the presentation. So again, the agenda, a little bit about cheatgrass for those of you who aren't familiar with the actual species. It's all about the data, method to the madness, results and model accuracy, and then conclusions and recommendations. And we'll take questions there, and hopefully you've got some good ones to provide some feedback. So what is cheatgrass? It's an invasive weed. We don't really like to refer to it as grass, but it's an actual weed. It's not native to North America. It was thought to be brought over through packing containers years and years ago, as the early tracings of it were mainly found along transportation corridors, both roadways and railway system across the country. The good bad is it's an annual grass. It grows in the spring, but it dies off pretty quickly due to lack of moisture. The downside to that is why is it a problem? When that dries off, it's a vicious fire cycle. So it's great for tinder, and because of it growing along roadways, places like that, all it takes is a little bit of spark, whether that be from a cigarette that might be thrown out the window to some type of a spark generated by a vehicle going by. But that tinder then takes off, and unfortunately, it's been traced to many, many wildfires across the country the last few years. So the purpose of our actual program here that we started in testing both in New Mexico and Wyoming was multiple agencies were trying to figure out how to go out and combat it. A lot of different places around the country have gone out and tried to apply chemicals to reduce or eliminate cheatgrass in their areas. And as they found out more and more, the cheatgrass was growing a lot more areas outside of where they thought. So the goal here is to actually identify where we have the invasive species and then be able to go out and eradicate it. On the left, here it is in its native. As you can see, it's already started to dry out a little bit. It's not quite to that tinder point, but this was flames from an actual fire out in Wyoming a couple of years ago that was traced back to a cigarette butt thrown out along the road. Ended up burning somewhere close to about 3,000 acres, most of which was cheatgrass infestation, but obviously it affected a lot of other plants that were in that, which then go into grazing and maintaining livestock, things like that, are then all affected by this. So a little bit about it. we're using elevation data, we're using imagery, and then ground truth. So for our studies here, we use QL2 Lidar, USGS QL2 Lidar data, which is at 2 points per meter or 0.7 meter nominal post spacing. And at the same time, we flew a camera with the LiDAR sensor. It is a 4-band, so red, green, blue, giving you the true colors along with the near infrared band. Approximately a half a foot was the ground sample distance that was co-registered and collected with at the same time. But to process, we actually need some ground truth data. So to train the computer model, we actually have to go out in the field and find areas of standing infestation, outline those areas, and then we can go in and train the computer model what it's looking for. So the key there is making sure that our ground trained data is acquired close to the same time that the LiDAR and the imagery are. So it doesn't need to be within a few hours. No, we're talking within a couple of months at the most is when we need to have that critical timing between both the acquisition from the air along with the data that's acquired from survey on the ground. Again, a couple of small areas that we did 3 years ago now out in Wyoming, and I'll go through a little bit more detail on those. Wyoming was a USGS project now wrapping up a total of 4 years to acquire all the LiDAR for the state. And we acquired co-registered imagery so we can actually look at the entire state of Wyoming. Their funding for statewide LiDAR was because they had people in the Capitol building that said, yeah, this is an issue. It's affecting grazing. It's affecting the tourism in the state and the fires, etc. So their portion of the funding for the state of Wyoming was funded with the idea that we need to find cheatgrass. So approximately 40% of the total cost of the LiDAR, USGS picked up the other 60%. As you can see on the map here, though, we've got 3 areas we did in the initial pilot. Go into a little bit more detail on those. Area 1 is approximately 5 square miles. It's located, again, we see this a lot in transportation corridors, so we picked some of those. So close to I-25, just outside of the town of Chugwater. Area 2, again, we picked it close to a road, but here we wanted something a little more remote. But more than anything, off to the right, you can see we're starting to get a little bit more mountainous terrain. So we also know that cheatgrass has a growing range in altitude. Most of it is below about 5,000 feet is where it's popular at, but the real popular sweet spot seems to be between about 1,500 feet and 4,000 feet in elevation. So that was the purpose of selecting area number 2. Again, another small 5 square mile areas. All these plots are about the same size. And then our third area, again, about five square miles. This is more of a rural farming area. And we're showing the effect of how the cheatgrass itself, and you'll see this a little bit later as we go through these presentation, but we'll find out how cheatgrass is moved not only by transportation and humans, but also it gets on animals, whether it's the seeds get in the fur or by their hooves. But it's very easy to move, and you can see the effects of that again in the slide coming up here in a little bit. So I mentioned field survey, so we have to go out and look at the locations. We have to find some ground truth areas. So again, here's an interstate area. The areas in blue that you see outlined there are areas where there is nothing but cheatgrass. So we went out, field survey, got the coordinates, excuse me, got the coordinates of those areas, and now we can use that data to train the model. This is just kind of a ground view of what those areas look like. Another one, as I mentioned, transportation corridors. You can see from the image in the lower left how it appears that somebody just drove by and scattered seeds along the edge of the road. Unfortunate, but that is some of how it still gets transported today is through trucking and vehicle traffic, moving it along the highways, because we're finding across the rest of the country, it's not just out west where this originally started, but we now have cheatgrass in all 50 states. But a lot of the eastern states, it is only within just a few hundred feet of roadways and rail transportation corridors at this point in time. We don't find it as remote as we do states west of the Mississippi. So method of the madness. So we acquire the remote sensing, and several of these different areas of remote sensing are applied to this. Slope and aspect, again, as I said, it's got an altitude that it really likes to, as far as a sweet spot goes. It's been found as high as 10,000 feet. However, most of it's less than 5,000 feet. but it also has a big slope aspect. It won't grow on a sloped surface that is extreme. It has to have a relatively flat surface so that that area, in theory, can capture water to be able to provide the nutrients needed to survive. Very heavy in what we call sagebrush steppe communities. Again, those are heavily grazed areas, whether it's for wildlife, from buffalo to elk to deer, to the ranchers out west using it for cattle. But very heavy in natural vegetation cover. Unfortunately, it's slowly pushing that natural vegetation out, reducing these grazing areas. The other is it seems to really pop up in a disturbed area. So where we found wildfires in the past or along development corridors, it's usually one of the first things you'll see growing unless steps are taken to go back and try to plant some type of a native grass in those areas, or continue to eradicate to keep the cheatgrass from ever germinating and getting started. So the relevant data, the source data, as I talked about, we have to make sure that we have good source data covering the entire area of interest. And then the timing of data collection, touched on that. Field survey, again, we go out and mark an area, provide a shapefile back to the guys doing the remote sensing work, and that's where they start into the training the data. So we're constantly basically telling the data, here it is, memorize what's in this shapefile area. And now, after it's gone through and classified all that data, the computer model is then run to go out and find additional areas that are very similar to that throughout the rest of the data set. From there, we go through and refine that data output, and then we establish an overall model accuracy. So it's a probability of cheatgrass. And as you'll see later on, the remote sensing we did both in New Mexico and Wyoming, we come up with a very high degree of accuracy. So again, the supervised classification, break everything down into little tiles, little squares, if you will, using both the imagery and the Lidar data. And we go out and those squares obviously cover those original shape files where we know cheatgrass infestation exists. We can go through that and identify that and classify that into different things. The elevation data also helps us because we can identify things like water and features above the ground. So cheatgrass by itself usually is found less than 3 feet in height. So we basically can set a threshold of maybe 5 feet and eliminate any vegetation that's taller than that as not being cheatgrass. We can also eliminate, so the computer model is not looking at anything that's on the actual Earth surface or the bare Earth surface. We also filter out and look at things like buildings and roads. So as we classify all these different things, we're also removing some of them from the data set just to allow the model to process, be a little bit more efficient. So here's a supervised, just the natural color imagery. Here's the area, again, along an Interstate 25. And here's the color infrared of that same area, showing more of the vegetation being popped up there. And then we'll get into more of a spectral analysis, combining both the red, green, blue, along with the near infrared. Here's our analysis. Again, the redder areas being very high probability of being cheatgrass. The areas in pink a little bit lower, or maybe a mix of cheatgrass along with maybe ventonata or medusa head or another invasive species that we see out there. So here's our actual supervised classification when we're done. A probability map. As I mentioned earlier, the areas in blue very low. It's the areas in red that are high probability, where those are probably and have been field verified after the fact that yes, those are nothing but cheatgrass. And then the yellow and the orange areas are medium probability, probably cheatgrass mixed in with additional species. So again, as we go through this output refinement, we continue to look at, okay, we're going to filter out all the highs, everything above roughly 5 feet. We want to very much look at the intensity imagery also with the Lidar data set. So we're using that to be able to identify where that canopy is at, along with areas that, along with another process that helps with the IR band to be able to identify that vegetation. Here's an example of a Lidar 3D point cloud. Again, the interstate you can see going across from left to right along the lower portion of that picture. And here's our Lidar point cloud of the actual interchange shown earlier of where we were looking at. Here is that same, again, using the elevation data only, the light from the Lidar point cloud, red being the taller grasses, yellow being the shorter, more than likely the cheatgrass or Medusa head or ventonata grasses that are found along the roadsides here. Again, back to a little bit of a raster probability mapping, the red being high and the orange being a medium probability. And again, this is the infestation results. Again, the more green being the high probability. So when we look at this is our second site. Again, more rural, a little bit of change in elevation. So here's our natural color, and here is where we see. And I'll go back and forth so you can take a look at that, because when you look at it here, you really don't see the difference from the image as far as saying, gosh, we really don't see much vegetation at all. But when we start doing the processing using the elevation, the infrared and the red, green, and blue channels, we can definitely identify areas where we've got invasive species or cheatgrass out in these areas. Again, here's our area number 3. Here's our natural color zoomed in from our previous picture. Looks like a little home here, but you can see there's a fenced in pasture area out in here. And what's interesting is as the animals move within that pasture, they've moved and the cheatgrass has moved and established itself of areas. If you look to the south and most of the north there, the cheatgrass infestation has not taken over outside of the pastured areas like it has the areas within the pasture. Just another example, this one we actually coated in the higher vegetation so you can see some of the actual sagebrush and evergreen trees that are out in that area. They now pop out a little bit as that rust colored on the left side of the image there. So what do we deliver? A 1 meter grid showing a raster probability from low, medium to high areas. Again, the high areas are usually from are going back out in the field afterwards. Areas where we are 95% confident that that's all it is cheatgrass. The medium areas are where it's usually a mix of cheatgrass along with other species of grass, and then the lower areas where there's little or no infestation. So again, the classification and accuracy, it's a basically analysis between the ground truth and the predicted probability cheatgrass. The survey crews that went out there did some blind data gathering also. So we not only captured data to train the computer model to what to look for and classify and identify as cheatgrass, but we also captured other areas that we were held back from the processing. We allowed the processing to go through and identify areas of probability, and then we brought back in the additional surveyed controlled areas. So we had a comparison, and some of those areas were nothing but cheatgrass again, but others were a mix of cheatgrass with other vegetative species, so that we can verify the overall horizontal accuracy along with the vertical accuracy required. So our accuracy assessment, again, for these 3 areas in Wyoming, the project there came out to about an 88%. When it was compared to existing knowledge of other areas on the ground. We didn't cover the entire 5 square mile area of each of those, but we covered about half as far as going out and in the field gathering information. Had a lot of help with the University of Wyoming and students there actually gathering that information for us. And again, the vertical accuracy is not much of a component. We're trying to find areas or something we can put a boundary or polygon around. So we really don't measure the vertical accuracy of it overall. It's more just the horizontal accuracy that we're interested in. So the conclusion, the assessment is a great template to use the imagery along with the Lidar to find areas of cheatgrass in the western United States. And again, we now have projects going on in New Mexico, Wyoming, Arizona, Idaho, and Montana at this point in time, trying to help them identify areas of cheatgrass along with ventonata, Medusa head, and several other types of invasive species they're trying to reduce or eradicate completely. And then, the other big one is the canopy height modeling, whether it's some people, when you hear canopy height, all they think is tree canopy. No, we actually look at overall vegetation. So whether it's trees or shrubs or all the way down to grasses, along with that slope analysis, those are used to augment that classification, which gives us the overall suitability model to be able to create the probability model. So some of the reasons for it, well, it's known to exist early. It's known to green up early. And unfortunately, then it also dries out when the moisture runs out in the spring. So again, we've worked with some of the staff at the state of Wyoming Fish and Game to identify areas. They provide a lot of past history. It's amazing the amount of information that's out there for year after year where they've collected it. They've seen it grow as far as an individual stand in size annually. But the thing that's been amazing to them so far is how many areas across the states that it exists. That there's no rhyme or reason to how it got there or how it continues to really expand year after year. The other is their sequence of growing is almost predictable. It's an annual. It comes out almost the same within about a 2 to 3 week period every year. Rise up, and then it transfers, and whether it's through animals or vehicle transportation or even just the wind. But it's amazing how quickly it can go through and go from green to being completely dried out and now just a tinder. The signatures of the grasses, again, we've collected those through a manual process out in the field to be able to train the computer model what to look for, and then we tell the computer model, here's some others. So not only do we capture cheatgrass out there, but we actually captured several other vegetative species so that we could then train the model and say, okay, here, when you find this, we know that it's a pine or some type of other shrub that gets excluded from the processing from here on out. And again, keeping that early to mid-season, so we want to capture the imagery and Lidar when the cheatgrass is coming out, when it's greening up, along with our survey data to be out there. So timing of the overall acquisition is very critical for the success of the mapping. And with that, I end my presentation. I will now open it up for questions. I'm going to go ahead and stop the sharing so that I can see the questions.
Don't be shy, everybody. First person.
See, Jerry, it's one of these. It's close to lunchtime. Some of them are just coming back, and they're kind of
Yeah.
lulled to sleep. So now I've put them to sleep for the rest of the afternoon.
Well, I find it hard to believe that you put them to sleep because this was actually pretty fascinating material to me. But I geek out on this kind of thing. So remote sensing is definitely my fixation with all of this. Oh, here we go.
Boy.
You do have a question in the chat. Did you use LiDAR combined with the optical data?
Yes, we did. So again, we use the LiDAR to filter out a lot of places where we know we won't have cheatgrass. So it identified all the areas where there's water because LiDAR doesn't return from water, so you end up with a black hole. So we could tell the computer not to process there. But probably the biggest thing, or one of the biggest things we used it for, was cheatgrass isn't known to grow very tall. So we also filtered out any vegetation that was above 5 feet. So again, it reduces the amount of time that the computer model has to go through. It also reduces a probability of it coming up with something that from a near infrared, it might be similar to what cheatgrass is, but due to the height of it, we know it can't be cheatgrass. And we also use the intensity imagery from the LiDAR. So yeah, but it's a combination of both the LiDAR and the imagery is what's giving us the ability to go out and find these invasive species and identify them. And again, so my first one, I think it's now 5 years ago, I got started with was cheatgrass down in New Mexico. We've also done looking for buffalo grass down in Arizona, ventonata in Idaho and Wyoming, Medusa head in Montana and Wyoming. So we're seeing it's not just cheatgrass that we can find, but many, many other variety of grasses, most of which that they're interested in though are invasive species that they're trying to eradicate.
We have a question from Nancy Reed. It sounds like timing is so useful. Could you do 2 collects and look for difference, or the collects by airplane?
Not sure if we were to do 2 collects, like say from year to year, what it's going to show us is, and what we've seen both on the ground and in the air, is that areas that are infested this year with it don't go away unless they're treated. They reoccur year after year, it seems like. Unfortunately, with that reoccurrence, is they also grow year after year. So we've actually looked at a small area I think our second area there, the pilot I showed, we have flown that. So the Lidar for the state of Wyoming is a 4-year flight. We went back to that area and reflew it every year just to determine how much it's growing or how fast that infestation grows when left untreated year after year. So again, the timing is more of it has to be in the spring as the cheatgrass starts to green up and take off to make sure that it's alive, so that we can use it with the infrared and the LiDAR data to be able to find it. But anything where we're getting successive flights is more just looking for how much of a larger area or how much of a bigger footprint does it have.
Now, the flights, are those ones that you guys are collecting the data, or you're getting the data from the state?
No, so these are Woolpert is a USGS contractor. We actually for those of you who saw the slide earlier today or the presentation earlier put on by the elevation group, we are doing the southeast driftless or the southeast corner of the state for the state of Minnesota under a USGS contract. So these are all USGS contracts where we're going out and acquiring it. We're also using some other states like Idaho. They've acquired it through multiple vendors over the years. We're just taking that data and going out and doing the classification and processing on it. We're not acquiring any separate data with that data set.
So Kate Carlson is asking, the supervised classification using NAEP for band imagery was enough to find areas of probable cheatgrass, or was there other spectral data included aside from the LiDAR verification?
We have not actually used any of the NAEP imagery, and it goes back to that timing issue. The problem with NAEP is they're they're more looking for crops, and most of the NAEP imagery is flown late summer or early fall, depending upon where you're at in the country. And NAEP of the western states is usually very late summer, and in that case, all of our cheatgrass would have already been dead or browned off. So it's the spectral analysis is going to be tough to do on plants that are dead. So usually, from what we've seen, we actually did a study trying to a small area in Colorado a couple of years ago, trying to use NAEP imagery out about 75 miles east of Denver, and it was a late August flight, and it was almost impossible to identify the cheatgrass areas. So unfortunately, NAEP imagery is not the best to be able to use for this.
Ken, I've got a question, if it's okay to just ask you, Leif Olmanson, with the remote sensing, a lot of times you'll use multi-temporal assessment to improve your classifications, just optical data. And with this, it seems like if you have a early greening and then a senescence, that would be if you could collect both of them, you could use the change to determine, separate it from other type of grasses, unless everything browns up at the same time.
No, you're right. You're absolutely right. The downside to that is then you've got the cost of 2 flights, and so we can extract out probably just as much data having those 2 flights as we can just having a single flight and doing processing a little bit different is what we from a cost benefit have analyzed on it. If you looked at a smaller area, and I know that there are different states that have done smaller areas. There's in fact some companies out there using drones trying to identify these, but unfortunately they're looking at acres, whereas we were looking at flying multiple counties every spring, and the cost to be able to fly a county in the spring, when it's all green, and then turn around and fly it a few months later is quite high compared to the rate of or the return on investment you get.
I'm not seeing any more questions come up. Thank you for the presentation, Mr. Park. It was more interesting than the title sounds.
Well, thank you. I appreciate being here. I will be around, and Woolpert also has a booth over in the exhibit hall. If somebody wants to reach out to me later, I'd appreciate it. But thanks a lot, Jerry.
Thank you, sir. As a reminder for everybody, don't forget the Remo exhibit hall for whenever you have a break, going over and checking out our vendors who are sponsoring all of this. So with that, I'm going to go ahead and now hand it over to Mr. Olmanson.
Yeah, thanks. Let's see. So I'm going to give kind of an update of what we've been doing using satellite remote sensing for water quality assessments, and specifically how we've automated the image processing procedures with the help of David Porter from the Minnesota Supercomputing Institute. So Minnesota, we've always been collecting lots of field measurements. As you can see from the Lagos data set, Minnesota has been an early adopter of collecting data, and they continue to this day. So we have lots of field measurements, which is really useful for trying to use calibration and validation data. Another example of that would be the Cyan project, where they gathered all the chlorophyll data they could find around the country. And as you can see from the map on the right here, that Minnesota is well represented in that data set as well. So with that great data, what we've been doing is we've been using the data, started out with just the Secudus measurements from citizen monitors. And then at the same time, we have satellites that are regularly collecting imagery. What we do is we take good clear imagery from a late summer index period, link that up with all the data within a few days of the image, build statistical model relationship, take that model, apply it to all lakes on an image. Do that for enough images, we come up with the water clarity for the whole state. Using that more manual technique, we've completed 9 statewide assessments since 1975. Each of these included over 10,000 lakes, and they were at around 5-year intervals due to the availability of the imagery and then also the processing it takes to do it manually. We use that for analysis, spatial temporal trends and causal factors. One thing we did back in 2001 is we made all of this data available in a lake browser. So it's like a Google Earth format, and people could zoom in on their lakes, get information about their lakes. Very popular with thousands of unique visitors coming to look at their information every month. Having this data at 5-year intervals has been great, but really if we want to improve lake and fisheries management, we need more water quality variables more often. And that's where we're heading with the new data sets we have available. So we have higher spatial, spectral, radiometric, and temporal resolution. So not only can we map water clarity, we can also map the factors that control water clarity, things like the chlorophyll in the water, suspended non-algal particles, and then dissolved organic color. So for the workhorse of remote sensing for the early years, definitely it was Landsat. With the Landsat 5 kind of having a really long lifespan and lots of imagery. Landsat 7 worked for a few years, and then it had the scan line corrector issue, so it still would work, but it has some missing gaps data, but still in good shape. Big change. The other one is the Sentinel-2. So we have some European Space Agency, a Copernicus satellite. They have Sentinel-2A and 2B. With Landsat, we have Landsat 8, and then Landsat 9 was just launched in September. So the Landsat data with the digital data sets would be, or the more let's see, the digital sensors of the new generation of satellite sensors is going to be 2 of them up at the same time. So every 8 days we'll be getting imagery, which will be a big improvement for the Landsat. With the Sentinel, it's at every 10 days for one satellite, but with 2, it's every 5 days, and with the overlap area, any 2 to 3 days. So big improvement in the temporal coverage. The characteristics that allow the satellite to measure different water quality variables is their spectral characteristics. So here I have some characteristic reflectance spectrums of different lakes in Minnesota. If you have a very clear lake, you're just going to have this peak at around 550 of the blue line here. When you have chlorophyll, you're going to have this characteristic reflectance spectra peak right here at 705. And then you have absorption at around 670. If you have cyanobacteria, blue-green algae, you're going to have this another dip here at about 620 nanometers. When you get CDOM, if you have just CDOM like this is CDOM, is the brown water tannin staining of water. And if you have really high CDOM, you're going to have barely any signal from the water at all. Very, very, very dark in the imagery. Once you start adding chlorophyll or suspended materials, that'll increase. But what it does is CDOM, it absorbs very strongly in the short wavelengths, and that decreases as the wavelengths get longer. So you can see how that interacts with comparing the green one with the yellow one here. You can see how it affects the signal when you have chlorophyll and CDOM in the lake. Sediment, if you have suspended material, non-organic, you're going to have it'll just be a peak across this whole area. It won't have the absorption trough due to photosynthesis. And this one is another one with high CDOM and suspended materials. So if you look at the characteristics of the satellites, so Landsat is missing that important red edge band. So that's a very important band for chlorophyll measurements. So with Landsat, works really good for water clarity, and it also works really good for the CDOM, but not so well for the chlorophyll. Sentinel-2, big advancement with the red edge band here. And then if we go to more of an ocean satellite, would be the Sentinel-3. It actually has that 620 for cyanobacteria. So let's take a look. The big advancement besides just the spectral characteristics is the temporal coverage. So we'll take a look at that next. So here's Sentinel-2A and then Sentinel-2B. And basically they're just continuously collecting imagery around the globe, and every 5 days they have the whole thing covered, which is a pretty big game changer for what we've been doing with satellite remote sensing, which I'll show you here in a second here with what we have in Minnesota. So this is the data from Minnesota. This is just August of 2019. So I'm just going to go through all these. One thing you'll notice is there's lots of cloud cover, and that's definitely most of these images I would not use. For the old manual techniques, I'd look for something like that with a very clear image, where most of these are a lot of work to try to deal with, trying to get rid of the clouds. So that's Sentinel. Let's do the same thing. So that's 2A and 2B. With Landsat, this is just the first satellite. So this is Landsat 8, and similar time period. And you'll see it's the data is a lot more sparse, and so the paths are not as wide, and so it doesn't get quite as much coverage. With 2, that'll double that, so that'll be a big improvement. But for now, it's kind of like limited, and for the most part, through Landsat's history from 1984 through all except for probably with Landsat 7 when it was first launched for 3 years in around 2000. There's only one satellite for Landsat, so that's how much data we have for the historical data. With the new data, we have big improvement with all of the more data. So the temporal coverage is really huge, and it makes processing the data, all this data, much harder too, because you have a lot more data to process. So really, we decided we needed to go for automated techniques, and so that's what we've been doing. It's collaboration between the Water Resources Center, the Department of Forest Resources, and the Minnesota Supercomputing Institute. So we have this opportunity for near real-time water quality monitoring, and so basically that's what we built. We had some funding from the Environmental Trust Fund in Minnesota here. And we have all this satellite data. It's downloaded to the ground stations. We have machine-to-machine access into the Minnesota Supercomputing Institute. Once there, we can do all of our image pre-processing, and this is what takes most of our time right here in this first box. Things like atmospheric correction. Instead of calibrating each image individually, we atmospherically correct. So we're normalizing all the imagery, and then we're developing a model for those atmospherically corrected images. And then we have to mask off things like the clouds, the cloud shadows, the wildfire smoke, and then just the terrestrial area. So it's just, and then aquatic vegetation is another one. So I'll give you some examples of atmospheric correction. So basically, atmospheric correction is basically removing the effects from the atmosphere. This is what the satellite will see. And what atmospheric correction does is it changes it to what you would expect to get on the ground. And so there's lots of different atmospheric corrections for water, and I've tested lots of them, and they all give different results. and some are much better than others. And so it's very important what atmospheric correction you are using. The other thing is the cloud masking. We tried a few different things with cloud masking and basically ended up starting with the FMask 4. Does a pretty good job of identifying the clouds and cloud shadows, but we had to buffer that a few pixels because there's always some artifacts around where those were identified. So we buffered that out and then did some additional masking to get rid of the additional haze over water and then aquatic vegetation and such. So our first our first try on that, we processed a bunch of imagery and worked out really well for most of the images, but we found some images had these anomalies. And so this first one right in the middle here, we found wildfire smoke was causing an anomaly. You can see how over water it didn't pick it up at all, but some of the terrestrials it did pick it up. So by missing the water, that was kind of a problematic for what we were trying to do. So we really needed to deal with that. So then we also developed some mask for smoke and wildfire smoke, and it's become a much bigger issue. The last few years has been ridiculous with the wildfire smoke we've had in Minnesota. Haven't seen that before, so it's been important thing to be able to take care of. So we're able to do that, and so once we have that, we have just clear pixels left, so we can build some water quality models. So our approach was for that is we basically linked up all available in situ measurements with all the available clear samples from the lakes, from the satellite imagery. And with that, for this is just 2019, we had over 6,000 Secudus measurements within 1 day of the Sentinel-2 imagery. This is just the Sentinel stuff. And then for chlorophyll, about 3,500, but this was within 3 days. We are still working on improving our chlorophyll model, trying to get rid of for the really low chlorophyll levels where we have very clear water. There's a little bit of a shifts from our 1-to-1 line, so we're coming up with some procedures for fixing that, but we have a good way forward. So good thing about our system is any model we develop, we can always tweak it and reprocess everything very quickly. So we have some models, we can apply it to all our imagery, and then we can make maps and data for use for different analyses and put it into our lake browser. So with that, show you some examples of the number of measurements we're able to get from, this is just Sentinel-2 again. This is for 2019, May through October. And throughout the state, we had at least 8 measurements statewide for every lake, which is pretty good, and had a lot more measurements than that, especially the overlap areas between 2 of the satellite images. See, there's a pretty big overlap area here, and that gives you a lot more measurements. What we found is we're able to make monthly mosaics seem to work really well, with a few holes once in a while if you had ended up with a lot of smoke or a lot of cloud cover for that month. But for the most part, it worked out well for making statewide maps. For any one area might have a lot more imagery that you could do, but for statewide maps, the monthly mosaics work well. And we're also able to extract the data for every single clear imagery. So we have a lot more data than just the monthly data. We actually have, the daily data when there was clear imagery. And then with that, we can calculate, anything. We could calculate a summer average, or we could calculate the monthly average, or, any delineation, deviation from derivative from that data set to come up with some maps for our analysis. So we have that for chlorophyll, clarity, and CDOM, which is color dissolved organic matter. So example of some maps. Here is this is the Rainy River and Lake of the Woods watershed up on the Canadian border of Minnesota. And it's a fairly pristine area, except for This is just 2019, but just except for Lake of the Woods and upper and lower Red Lake here are known to have some turbidity issues and cyanobacteria blooms in the Lake of the Woods. I'm going to do this one more time. There's this one red dot that shows up right about, where is it? Right there. So it shows up in here. You know, out of all these lakes, there's over 10,000 lakes in this watershed, and you know, most of them are fairly pristine and not really having too many issues, but that one kind of showed up, and took a look at the satellite imagery, and actually there was a bloom on that lake, on Laureley Lake, August 3rd, 2019. So it's kind of neat how you can, you know, look at over 10,000 lakes and pick out something like that. So here's a little bit more exciting area. This is the Twin City metropolitan area. This is from May 2017 through to October 2020. And again, the open water months. So I'm going to start this. So for May, the Sentinel satellite just started operating in the United States. Well, I think the first one was launched in 2015, but there really wasn't a lot of data collected over the United States. So really it was by September is when it was in full operation for the data sets, which you'll kind of see a few holes sometimes for this early period. And then after that, it's pretty consistent. You'll notice lots of blooms in the agricultural areas to the south and to the west of the Twin Cities, and then some of the lakes in the Twin Cities. So very dynamic systems. So we have monthly mosaics for chlorophyll, clarity, and CDOM for over 10,000 lakes, 2017 to 2020, and we're just completing the processing for 2021. After October, I guess we're getting close. After Sunday, we'll have all of the imagery we need to complete that. We can also look at the daily data. So here's some examples of the daily data. So this is Lake Francis. We have more of a mesotrophic lake. Tatanka, more eutrophic. Lake Washington, getting more eutrophic. And then Cicada, peeking into the hypereutrophic. German, and then Elysian, which is a hypereutrophic lake. So we have that. We got that for all the different years, and you can see differences from one year to another. You know, different seasons, different temperature, different precipitation will change how lakes react. So having that data can be very useful. And here's monthly data. Whoops. Monthly data for those same lakes. You can see the general pattern for the seasonal change for that. So for our spatial and temporal analysis, we have this new data set. Then we had the manual technique methods for the earlier years, 1985 to 2015. And basically what I did is I calculated the late summer index period. So it's a July 15th through September 15th period. And then basically calculated that for all these years and then looked at spatial and temporal trends. Here's the late summer 2000, some whisker plots showing the distribution. The northern lakes and forests have some of the highest water clarity in our state, and that's where most of our lakes are. So that's the lakes, wetlands, and forest area. So pretty pristine water. The northern lakes and north central hardwood forest ecoregion is more of a transition zone. So it's got about 50% agriculture, but still a lot of lakes, forests, wetlands. So that's pretty good water too for a lot of lakes. And then we get to the more agricultural areas, and then you have the lower water clarity for those. So we look at trends. So we looked at all the lakes from 1985 to 2020, and found that about almost 20% had a change of 10 TSI units, which would be equivalent of a doubling or a halving of algal biomass, or a doubling of halving of a Secudus measurement. So fairly significant changes over that period. We found about 14% actually increased water clarity, and about 6 decreased water clarity. If we take a little bit finer slice, 5 to 10 TSI units, so not quite having or doubling, but still fairly significant. We found about 26% changed that much, 18% increased, and about 8% decreased. So if you look at the statewide distribution, what we find is a lot of the agricultural ecoregions seem to have, for the pie charts, you can see higher percentage of decreasing water clarity lakes than improving, and more improving water clarity than decreasing in the other areas. With looking at some of the lots of improvement in the metro area, my assumption is due to probably the all the storm ponds and the work that's been done in suburban and urban areas to improve the water quality. When you get out into this area, a lot of agriculture out in this area, and then it's the prairie pothole region. And there's, I'll show you a little bit later, but there's a lot of change in precipitation in this area. And so there's a lot wetter coming from a dry period to a wet period, and that can cause some changes and in the water quality. And then also in the southern Minnesota, a lot of agriculture kind of going both ways, but there's a few more decrease in water clarity there. With the one thing that kind of concerned me was this area up in northern Minnesota. It's a fairly pristine area, the lakes, wetlands, and forests, and it's kind of widespread area. Most of these are the smaller, shallower water bodies, so the ones that are more susceptible to change. So it started looking at what was causing those changes. First thing I looked at was temperature. This is late summer temperature, just August, September, and to match up with our water clarity data. And we found there's a 2.6 degree increase over the whole state of Minnesota over that period. So pretty significant increase. And then also the precipitation, we've had some big swings in dry and wet periods over this period. And so it's, kind of a wider fluctuation. So things seem to be changing a little bit, and it could be part of the impact from that. So we also looked at other variables. So looked at land cover. How has land cover changed over this time period? So use the new LC map product, which is yearly from 1985 to 2019, I think is out now. But that'll be continuously updated. So it's kind of a neat new product. The classification is fairly simple, but pretty good for lots of different things. So basically what I did is I just looked at a change detection with the pixel level, and then quantified that at the catchment level, which is our finest delineation for watersheds in Minnesota. So the first with going from shrub to shrub and grass and shrub. So that'd be basically areas that were harvested. So forest harvesting up in this area, and then regeneration would be the grass, shrub, the tree. And so it's kind of a higher percentage of harvested lake or harvested versus the regenerated ones over this time period. Some of those are in some of that area, but a lot of those areas where there were change that weren't, haven't had that big change. So that was the major change up in the northern part of the state. There's other things going on, like going from forest to cropland, which is a big concern for lots of people. Developed areas, some of the areas that are being developed, the metro area for sure, and then a lot of the medium-sized towns are actually getting bigger too. Big cities, I guess, major city hubs are actually expanding quite a bit over this period. Mining operations up on the Iron Range, that's had a impact up there, and then to cropland, so the areas that have gone to cropland are here. And then to trees, lots of trees like around the suburbs and around the metro area have increased some tree in some of these areas. So that could be a change to watch. Other thing, water, here's, I said that, the water is changing, so there's more water out in these areas. And then wetlands as well. Changing. So some examples of some videos. So this is northern Minnesota, kind of showing some of the forests going to the grass shrub, and kind of watch how that goes. So the areas that are getting lighter are the areas that have been harvested. And then we got Hubbard, Wadena County, and seeing some of the forest areas changing into cropland. And then out in western Minnesota, where the prairie potholes are filling up with water, you can kind of see how that is changing. So some different some major changes over that period. Other things, looked at the precipitation and temperature, and this is the precipitation, much higher in southeastern Minnesota than northwestern Minnesota. But the change, a lot of the change, more water in this area that we're talking about with the prairie potholes filling up, but drier up in the Arrowhead area. Look at temperature, much warmer in the southern Minnesota than the Arrowhead area. And if we look at the change, significant changes throughout the state, but the most, I think it's the fastest warming place in the United States is actually this northern part of Minnesota. So fairly significant changes up there. So definitely could be part of the why things are more blooms now than there was in '85. So here's that chart again. And I'm just going to go to some of the crops, how the crops have changed as well. So we've gone from kind of a mixed with small grain and corn, soybean, and other crops to mostly corn and soybean over this period. And if we look at how that goes at the county rate, big increases of corn in this area where a lot of those decreases in water clarity were in the western Minnesota, and then increase in soybean in the Rainy River, Red River basin up here. And if we look at small grain, big decrease in big decrease in small grains in this whole area. So the crops are changing, and so moving more towards more intensive agricultural practices. And other crops are also decreasing in southeast and central Minnesota. And if we look at animal units, big increase in central Minnesota, and then in southern Minnesota, and the decrease in the northern part of the state. I have done a spatial type analysis. I did one going from 1985 to 2015, and I'm in the process of updating that to go to 2020. So basically the way I've been doing these is I've been linking it to headwater catchments. So it's only the headwater catchments, so which would be basically the watershed for that specific lake, and then linking it with the land cover change, and then temperature, precipitation, and then other things like the animal units and the county level harvest data and such. Like, there's lots of different things we can put in there and kind of see what's going. I don't have time to show you the results of that, but I'm kind of running a little bit over, but I think I'm gonna show you our lake browser. So here we have the new lake browser is available. All of our data is on there that we have processed so far. Oops, I'm gonna put this right over here so you can actually see it. We have clarity. We can pick different years. We can pick pixel level or lake level data. And then we can pick different months. So we can zoom into different areas. And so every lake in the state, anyone can go and go to our website, and they can actually get information about a lake. So I'm just going to click on Lake Minnetonka, with popular lake in Twin City metropolitan area. It's got a improving water clarity trend. You can see, we have data going back to 1975 for this, and you can see how it's changed over the period and how it changes from, with the more recent data, a lot more often. We have the monthly data on here now. So for the last 4 years, and then it's all tabulated here. We have the seasonal. What we used to do is the late summer, one time a year, every 5 years. Now we have it every year, every month. So big increase in the data sets that are available. We rank them. How does it rank statewide or county? You can see how that lake ranks in the state. We also have all of our daily data here too. So every measurement for clarity, chlorophyll, and CDOM is in a big table here that you can look at. We have the chlorophyll seasonal values and then the CDOM. And then we have land cover, so you can kind of see, what the shoreline is like for that lake as well. So it's very useful. We've found it to be very popular. So I think this new data set should actually improve it quite a bit. We just added all this this summer, so big improvement there. So you can go up to things like the St. Louis River Estuary and Lake Superior. You can see different seasons, see how things change. There's lots of inorganic suspended material that comes into Eloise Bay, Pokegama Bay, and you can see how it affects Lake Superior on this lake. So that is that. And then let's see, we have looking at other areas as well. We've been doing South Dakota, Wisconsin. Some examples there. And then we're testing it out in down in south in Georgia and Alabama, some of the reservoir systems, which is kind of neat. They have a lot more clear imagery down there. So it's, you have a lot higher temporal coverage, and some of these pulses of the sediment plumes coming in is kind of interesting to see on that. And with that, I will take any questions. I guess I went a little bit over, but I think we still have time since we are missing our last person.
Oh, we had a cancellation, so there is some leeway here for you.
So
I don't see any questions popping up just yet. Don't hesitate, everybody be throwing something up. I do see a remark though from Nancy Reed, remarking about very interesting to see the changes since 1985.
yeah, that's it is. I mean, definitely there are changes, and trying to get exactly what's causing them. I think there's lots of different factors causing them. So trying to nail it down to one thing is probably not possible, since every lake is kind of unique, but there definitely are some trends, like with the prairie potholes regions, where you have going from a dry area to wet, and then going from probably small grain to corn and soybeans definitely can have impact. With the northern Minnesota, I think a lot of that is due to temperature, and then some of the harvesting, of course. I think the temperature it is astonishing, and we definitely have climate change in Minnesota. So and we're gonna, our impacts are some of the most in the country. So it's definitely, we will see it, and so I think we need to, probably a good time to be monitoring our lakes at a very good, strong, high detail like we are now. Yeah, I think a lot of the field that we're doing a lot of collections for all the CDOM and stuff back in some of those 2016, 2017, and all the storm events. It was really big storm events, large rainfalls, and it's been very very dramatic weather for some of the years. So
I think one takeaway that I have for myself, and I'll share this with the group, is that remote sensing that we're looking at with all of this is very instrumental in being able to understand our world, whether it's Mr. Parks's presentation having to do with the spread of invasives, or whether it's your presentation on monitoring lake quality, water quality in various watersheds in our regions, and just the fascination that I have with being able to not only see the world, but be able to use the technology we have to see the world in different ways to better understand it. And that to me is the most, I guess, exciting thing about the remote sensing field.
Yes, I agree. Especially with the new satellite systems we have, we can see, a lot more, measure a lot more things, a lot more often. And the temporal coverage is always the thing that's been missing with the remote sensing. And now that's not as big of a problem, at least for the small, the smaller lakes and stuff. There's always been the daily ocean satellites, but for monitoring most of our lakes, it doesn't do much good, but the Landsat and the Sentinel-2 are great sensors to have.
Well, we definitely have gone from the age of Victorian era of the one gentleman scientist in his little shack measuring the temperatures and the rainfalls in this tiny little spot and never really meaning anything, to now having the ability to look from above and be able to measure everything we want to measure within the limits of the technology, and the ability to have that data and to be able to extract information from that, and actionable information from that, is mind-blowing to me.
Yep. Yeah, no, I agree. It's I think there's a lot, because you can pull in all the hydrology talks with pulling in all the weather data. And one thing we were kind of looking at is actually pulling in a lot of the weather data to be able to model the lake temperature. So you have the water clarity, which is part of so the clearer lake versus a more cloudy lake will react differently to different water clarity. So it'll absorb or transmit more heat into the lake. And but having the weather data, you can actually model, you can improve the lake temperature models, but then also you could use it to kind of predict where things like harmful algal blooms would be. So there's lots of things you can start pulling together. And then the precipitation would be another thing, pull that in there with the runoff or whatever. There's all this technology can come together with one big model, all the different pieces that need to be put together though. So lots of exciting things to do in the near future.
I've not seen any more questions pop up, so I would like to thank Leif, David, and Kent for being with us today and having given us the chance to be able to learn from them. This is, again, to me, the stuff I geek out over. So this has been an honor and a privilege to be able to hear you guys present. Thank you so much. Unless anyone else has anything, then I'm going to give it a few moments. I'm going to close out the session. Thank you, guys.
Thanks, Jerry.
Thanks, everybody.
Thank you.